everyone, my name is Ying Tong and I'm a core developer at the Electric Coin Company, and this is the Halo2 ecosystem showcase. So Halo2 is a proving system that allows for recursive proof composition without the need for a trusted setup. And this has already been deployed in Zcash's network upgrade 5. And it's the proof system that's underlying the Orchard shielded payment protocol. So Halo really got its start in 2019 with this paper by my colleagues Sean, Jack, and Dara. And since then, it's seen a bunch of citations and a bunch of work from the academic community, including Halo Infinite, as well as proof carrying data from accumulation schemes, which is a formalization and a generalization of the construction in Halo. We've also since implemented the Halo protocol in the library Halo2. And it's called Halo2 because we've replaced some parts of the protocol with more efficient and newer schemes. And since then, there's been 132 forks and counting, and it's been used by 203 people with 22 contributors. So today's talk really is about how Halo2 has been used in the community and how the community has been contributing and improving Halo2, as well as our plans for maintaining the library and merging these contributions and taking Halo2 further. So yeah, Halo2 is not meant to be just a Zcash library. It's meant to be a general purpose proof system that can support many use cases. And that's why we're interested in maintaining the ecosystem and encouraging contributions. So when I think of contributing to Halo2, I think about it in terms of there are different levels you can contribute at. So for example, at the protocol level, really you're making changes to the proof system itself, like to the math. You're introducing, for example, a different polynomial commitment scheme at the back end. Or you're changing the prover, you're introducing a multi-phase prover. Or you're changing the nature of the lookup argument and allowing it to support more dynamic use cases. So we'll be going through all of these in the presentation. So that's the most fundamental, the lowest level at which you can contribute to Halo2. One level up is what I think of as the circuit level contributions, in which you basically change the way we're using circuits or thinking about circuits. So for example, we'll see a bunch of circuits that make use of the configurability of Halo2 to optimize for a fast prover or fast verifier modes. And this was something new that the Zcash team didn't need, but external contributors found the need for. Another example of a circuit level innovation is cross-circuit lookups, meaning allowing circuits to interact with each other through the lookup argument. And we'll see an example of that as well. And again, this is something that was not needed by the Zcash team and was contributed by external developers. The third category is dev tooling, and this is absolutely crucial to the growth of the ecosystem. So one example is improving the language and the arithmetization, or basically the development front end, which developers use to write circuits. And on the highest level is applications. And this is probably the most fun level because this is where you can make games and things like neural nets, hash functions. You can put whole virtual machines into Halo2 circuits, and people have. And yeah, so we'll be looking at these contributions today. So the first type of contribution, protocol. Yeah, probably the most fundamental change I've seen in the wild to Halo2 is the replacement of the polynomial commitment scheme. So Halo2 uses the inner product argument to commit to the polynomials that represent the relation or the circuit. And this inner product argument then allows us to instantiate an accumulation scheme. So I've seen a project basically abstract over the polynomial commitment scheme and to make the API generic over either the inner product argument or another scheme called the KZG commitment scheme. And this project is the zkEVM project, or one of the zkEVM projects. So if you're not familiar with what a zkEVM is, it's basically a layer 2 on Ethereum that is running the Ethereum virtual machine's full state transition function. And so for each state update on the layer 2, the zkEVM makes a proof that the whole state transition function was fulfilled. And yeah, this involves putting the whole Ethereum virtual machine into a Halo2 circuit. So this is a huge circuit. By far the most ambitious project I've seen that uses Halo2. So the reason why they needed a KZG proof instead of just an inner product argument is because Ethereum specifically has a precompile that makes verifying the KZG proof very cheap. So it's when these context-specific requirements are introduced that we see very interesting abstractions and modifications of our protocol, and we see how to make our protocol more generic and more usable by people. Another protocol level change was introduced by the same project, and this is the multi-phase prover. So what the multi-phase prover is a generalization of our current provers. So right now, how the prover interacts with the protocol is that it generates a witness of all its secret values. We call these advised values, and it commits to them. And then using these committed values, the protocol derives a random challenge that is then used to combine constraints and polynomial relations on the committed values. So it's very important to note here that the randomness is derived only after the values are committed, which means you cannot go back and manipulate the values to produce some favorable randomness that allows you to basically trick the protocol with a pathological witness. So the point of the commitment is that the challenge makes the advised values irreversible. So what the multi-phase prover does is it chops up the commitment phase into multiple phases. So instead of committing to our values all at one go, we split up our columns, we split up our values into phase 1 and 2, say. And in phase 1, we commit only the phase 1 columns, values, and derive a random challenge, which we can then actually use in the rest of the protocol. For instance, the random challenge can participate in the value of a phase 2 column, for example. But in phase 2, we cannot then go back and change values or write over values that we had already committed to in phase 1. So this is an important generalization because it enables a range of use cases. So it enables you to basically shuffle your witness or to enforce some random linear combinations or random relations between your witness, where it's important that they're combined using some randomness that is the result of committing to the values themselves. So again, it's the zkEVM project that came up with this use case. And they needed this because, for example, in the Ethereum virtual machine, each word is 256 bits, and that can't fit into a field element. So instead, they cut up each word into bytes and provide just a random linear combination of those bytes. So they used the multi-phase prover to produce that randomness. So those were the protocol level changes, and to me, these are very interesting and very fundamental changes. Arguably, they're also the hardest changes to merge upstream. And our philosophy when it comes to protocol level changes is basically, is it popular enough? Is it a general enough use case? Would people find a multi-phase prover useful, or would it just be a distraction if most people use a single-phase prover anyway? So these questions are basically, we need the community's input on these questions, and yeah, we have discussions about this on GitHub. So on the next level is what I think of as the circuit level. I probably could have named this better. What I mean is thinking about programming circuits in a different way. So for example, Halo2 provides a lot of flexibility to the circuit writer. And in particular, it allows you to configure the shape of the circuit, where the mental model here is a two-dimensional matrix. And you can either have a circuit that is like long and thin or short and wide. And the implications of that heuristically are as follows. So the shorter your circuit, the faster your prover. And that's because fewer rows translates to smaller FFTs that the prover has to do. So faster FFTs. Whereas on the other hand, if you went for a long and thin circuit, so fewer columns and also fewer constraints, then that actually makes for a faster verifier as well as a smaller proof. But the trade-off there is that you would probably have to use more rows and have larger FFTs and a slower prover. So the implication of being able to configure for the prover versus the verifier is that in, for example, a constraint verification setting, like verifying on a smart contract, you want to definitely configure for a fast verifier. And these two examples are from wrong field arithmetic libraries in Halo2, where basically the writers tried to minimize the number of columns and the number of custom gates used. I didn't include it in this slide, but you can compose fast prover and fast verifier configurations by using fast prover circuits at the base level and then recursively aggregating them in fast verifier circuits, such that your end result, the recursively verified proof, is fast to verify. So Halo2 unlocks this level of optimization, and it unlocks a whole range of strategies for the circuit writer. Yeah, and as I mentioned before, this use case would not have arisen from just purely the Zcash orchard circuit. And in fact, it's this project again, the zkEVM project, that saw the need for this use case. The zkEVM circuit is so gigantic that they had to basically break it down into many smaller sub-circuits. So you can see here the leaf circuits the leaf circuits here should be fast verifier, should be fast prover. And then the top level aggregation circuit that links them all together should be fast verifier, because that's the circuit that produces a proof that is ultimately verified on a smart contract. So It's an extremely constrained verifier, and every field operation it does cost you real money. It costs you gas. So another example of a circuit level innovation comes from the interaction between circuits. So when composing these circuits, we need to additionally check that some relations hold between them. So for instance, in the zkEVM, some circuits have to share certain values from the same lookup tables. And we need to basically check that they are in fact using the same lookup tables. And this is a sort of relationship that we're reasoning about at a super circuit level. So we can only access cross-circuit information if we go one level above to the aggregation circuit. And so I think Jordi from Hermes, who may not be here, he's writing up something called Rapid Up, which sort of formalizes the cross-circuit lookup argument and introduces several optimizations for it. So this is another example of a circuit-level innovation that Zcash alone wouldn't have come across. And the final circuit-level innovation that comes directly from cross-circuit lookups is dynamic lookups. So this is somewhat just an API quirk. Basically, in Halo2 right now, we support lookups only for a subset of values. So we only support using fixed values as lookup tables. Fixed values meaning they're hard-coded in a circuit, and they're known they're publicly known independently of the prover's private witness. So we introduced this API restriction for safety purposes, but almost immediately we found that the forks of Halo2 had to revert this change because they had the use case of lookup tables that were themselves witnessed values. So we're doing some work with these groups to generalize the lookup API and to support advice columns as well as instance columns as lookup tables. So those were the more fundamental kinds of changes that if we merged, it would pretty much affect all downstream consumers of the API. But when we get to this class of changes, dev tooling, I think this is truly the most underrated type of change. And at the same time, it's one of Halo2's biggest advantages, is that we pay a lot of attention to the developer experience. So I think I showed you just now the level of flexibility that the Halo2 API affords the circuit writer. But what this means as well is that writing Halo2 is like writing assembly. Basically, you're assigning a lot of these values manually, and you need to be strategic about the regions and the rows and columns in which you're assigning them. So this can lead to quite just a not fun developer experience. And so there's been a lot of thought into how we can express these circuits in a higher level language. So Orbis Labs is a project on Cardano, a ZK rollup on Cardano, who have been building on Halo2 and who have been thinking about this problem of higher level arithmetization. So they came up with this paper a few months ago called the Sigma 1-1 arithmetization, whereby basically you go from a relation to a Sigma 1-1 formula. And then from a Sigma 1-1 formula, they define like basically a protocol you can follow to end up with a Halo2 circuit. So this might not be the most optimized and the most efficient arithmetization. However, the sigma 1 formula is amenable to more kinds of analysis, formal analysis, and optimization at that level. And just, I think 3 hours ago on Twitter, I saw that Orbis Labs posted the Orbis specification language that builds on top of the sigma 1 arithmetization. So it's an even higher level language. It's way too small on this slide, but and anyway, I haven't had time to read the paper. But this is an example of how you would write a Sudoku circuit using the Orbis specification language. So we're definitely excited to see Orbis building abstractions in higher level languages on top of Halo 2. And this effort of finding better intermediate representations is something that would interest all projects that use Plonkish arithmetization. So for example, Anoma, who presented Taiga yesterday, is also thinking about this, and we would love to collaborate with them. Another example of great dev tooling is by this project called DarkFi. So they've built a compiler and a VM called zkAssembler. So basically, what this consists of is firstly a DSL. Yeah, you can see here a very succinct DSL that expresses an arithmetic circuit, so doing additions, multiplications, subtractions, and comparisons. So under the hood, this DSL links to basically precompiled chips in Halo 2. So an addition chip or a multiplication chip is going to carry out these instructions and is going to enforce the constraints under the hood that basically encode them in the circuit. And on top of this DSL, DarkFi actually built this inspector that can go through the stack and just show you the trace, the execution trace, and show you what's happening at each stage of the VM. So this is super cool. We don't have anything like that in the Halo 2 upstream. I think that's because we haven't defined a virtual machine like they have. They defined a virtual machine just for a subset of the most commonly used operations, like elliptic curve cryptography. What else? Like hash functions and all that. Yeah, but we haven't, in Halo 2 upstream, we haven't bothered to write a DSL or a library integration like that yet. But I thought this was really cool. Yeah. So we get to the final layer of contributions, and this is the application level. So recently, there was this summer learning group, Halo2 Learning Group, organized by a ZK collective called Xerox PARC, where participants just hacked on Halo 2 and built fun things on top of it. So this right here is a ZK Wordle that's running in the browser. So it allows you to prove that you actually guessed the word in as few guesses as you claim. And this is definitely a higher level of assurance than just copying and pasting the emojis. So this was also innovative because, to my knowledge, it was the first end-to-end demo of Halo 2 in a browser. So it required generating Halo 2 proofs and verifying them in WASM. And this is an integration that Zcash also had no use for up to now. And we wouldn't have had this if not for this third-party contributor. So you should check out ZK Wordle. The proofs take a little while to generate, but it's worth it. And Xerox PARC produced really a great number of innovative applications. So shout out to them here. Some of them include, for example, deep learning or a convolutional neural net in a Halo2 circuit. Someone did MIMC and MIMC Faisal, which is a snark-friendly hash function. And outside of Xerox PARC, independent contributors have also made, for example, Verkle trees and generic Merkle trees, which are greatly useful primitives. And in addition, Orbis Labs is building tiny RAM in Halo2 for their rollup on Cardano. There's also a bunch of upcoming projects that the Xerox PARC Learning Group participants are planning. So for example, state channels in Halo2. For example, introducing better primitives for matrix multiplication and FFTs. Or like integrating Zcon3 proofs into Halo2 and being able to aggregate them. So I'm excited about any project that increases interoperability between Halo2 and other proof systems. And Bitcoin VM is another exciting project that's being planned. I also want to give a shout out to this repository, Awesome Halo2 on GitHub, which compiled a bunch of these projects as well as useful resources. So I'm done with the contribution part of my talk, and hopefully it's become clear just the diversity of use cases and features that enrich the Halo2 library and that come entirely from external contributors that I think make the Halo2 ecosystem really fun and really strong, basically, and able to serve a larger group of use cases. So that being said, the Halo2 roadmap is, we do have a few concrete milestones that we want to hit. Apart from serving the ecosystem and merging these contributions, our priorities on the protocol level for now is to implement recursion. So Halo2 in Orchard right now does not have the accumulation scheme level. So we're not recursively composing our proofs right now. And in order to support that, we have to make a few changes to the protocol. For example, to make a pluggable API for proof generation, as well as a bunch of efficiency fixes. To just make our circuits efficient in the recursive setting. And on the circuit level, we have to make a bunch of changes to our circuits to make them generic over the curve cycle. So Halo2, the recursive Halo2 actually works over a cycle of curves, whereas Halo2 in Orchard right now is implemented entirely only on one of those curves. So we have to take all our circuits and make them generic to both sides of the curve. And that's really not as straightforward as you might think, because these curves have different base fields and scalar fields. And in particular, the base field of one curve is the scalar field of another. And so wherever we assumed that the base field was smaller than the scalar field, we have to get rid of that assumption and no longer rely on it. And that complicates some parts of elliptic curve cryptography, for example. We also have to implement, again, efficiency wins for recursion. So in Halo2, a big overhead of recursion is from communicating deferred arithmetic from one side of the curve cycle to another through public inputs. And so we're implementing endoscaling for more efficient communication of public inputs. We also need to adapt some of our primitives, for example, the Poseidon hash, and we have to basically make them usable in the context of a transcript, the Fiat-Shamir transcript used in recursion. On the dev tooling layer, from our interactions with the community and also from our own user experiences, we've identified a whole bunch of tools that would greatly improve the experience of writing circuits and also make it a safer process. So yeah, I'm not going to go into the details of these, but I've linked the issues here so that you can check them out. Or you should also check out Strat's talk that's going on right now. But don't go right now. Because Strat goes into the details of how circuits in Halo 2 are laid out. And there's basically lots of optimizations left that would make the circuit layouter more powerful. But I do want to emphasize the last point, which is the exploration of some intermediate representation or higher level language. There's been a bunch of projects already interested in this. For example, Orbis, as I mentioned, and for example, Anoma or Taiga, who presented here yesterday. And it would be great to get some working group together where we could agree on a set of requirements and agree on a spec. So that would help the developer experience greatly to not have to worry about too low-level concerns. And finally, the applications that we have in store. Well, first of all, Orchard, the shielded payment protocol in Zcash, is the main application of Halo 2. And besides that, we have our project with Filecoin to use the recursion to compress the proofs. So Filecoin, the blockchain, is full of proofs. Proofs of space-time, proofs of replication, basically proofs that the storage providers are actually storing your data. And these proofs are so numerous that they take up really a significant amount of space on Filecoin. And therefore, Halo 2 can help to compress these proofs with unbounded recursion, basically, and reduce the space usage on Filecoin. Another application that's coming up is actually in partnership with the Ethereum Foundation. So they use a verifiable delay function as part of a randomness beacon construction when selecting validators in ETH 2.0, proof of stake. And it's really important that this selection process be random and that the VDF construction be as efficient as possible. So introducing a recursive snark would mean that the VDF verifier gets an exponential speed up over the VDF prover. And finally, an application that I'm excited about is ZSAs, Zcash shielded assets, which Kedit is working on. Yeah, that I expect that would only involve changes on the top level API level. Yeah, I don't even think they would have to introduce many new circuit components, hopefully. Yeah. So that is all I had. This is the Halo 2 ecosystem Discord that we just set up today. So on this Discord, we're going to basically be available to discuss any questions that you might have and to respond to feature requests or even just as a space for you to share the things that you're building or the moonshot ideas you have or to just hang out with other people who are also building on Halo 2. So please join us on this Discord. And we also have a weekly Halo 2 office hours every Tuesday where you can, just come and hang out with us. Thank you.
So we've got several questions. The first one, are there any direct benchmarks between Halo2 and other Plonkish proving systems?
Yeah, that's a really good question. I recently saw on Twitter someone wrote SHA-256 in Halo2, Plonky2, and Zcon, and they benchmarked proving time. So yeah, basically when you move across different Plonkish proving systems, you get different trade-offs. And Plonky2 in particular is optimized for the fastest proving time possible because their field is very small, 64-bit field. And that fits in a word in most architectures. So whereas Plonky2 produces larger proofs, so it would be slower to verify. Whereas for Halo2, our proving time is not as fast because we are still working over large fields, elliptic curve, like 254-bit fields. But our proof sizes are smaller. So this benchmark that I saw on Twitter, SHA-256, had a 10x speed up when implemented in Plonky2. Yeah, but the other sort of Plonkish implementations that are very competitive are Aztec's Baratenberg. So Aztec is the originator of Plonk, and they have a super fast C++ implementation. Yeah, basically, I think when it comes to benchmarking, you need to ask what you're benchmarking. Yeah, if you only care about or you mainly care about prover time, use Plonky2. Yeah, if you care about proof size, use Halo2. Or you could use Aztec's Plonk, but that involves a trusted setup. So if you care about not having a trusted setup, then also use Halo2. So really, my long-winded answer is that you should bench with purpose, and benchmarks are only useful insofar as they inform your particular use case. Yeah, and also I encourage everyone to please benchmark different Plonkish proof systems. I don't think enough benchmarks exist right now. Yeah.
TinyRAM was meant for R1CS, while Halo2 uses Plonk arithmetization. Have you thought that the set of instructions could be extended or improved using Plonk?
That is a great question. So firstly, I'm not the right person to answer this, and we should definitely ask the Orbis team who has implemented TinyRAM. But in general, yes, I would imagine that that writing TinyRAM in Plonk opens up a bunch of optimization possibilities. For example, you now have lookup tables where you didn't before in R1CS. You have copy constraints, you have custom gates. So whether or not these help TinyRAM become more efficient, I don't know. I don't know TinyRAM well enough. But it's a great question and a great intuition to have. Like, you should move to a different proof system because it makes your use case more efficient.
A Discord user says, I'm surprised to see not as much work on incremental proofs or application level recursion, basically. Any thoughts on this?
Well, I'm not sure. This is how I'm interpreting that question. I'm interpreting it to point to the fact that we've not yet deployed recursion in Halo2. And we've only deployed the front-end arithmetization and the polynomial commitment scheme, which is the inner product argument. So most definitely, recursion is our top priority now. It's what all the open issues are about in the Halo2 library, and we're working to implement that. maybe one thing that had slowed us down, and I think rightly so, is that we took some time to make a security proof of Halo2, which meant also making a security proof for Plonk, which to our knowledge did not exist before then. So my answer to that is we are prioritizing it and we're working on it and we want to do it in a safe way. Yeah.
Awesome. Last question. What kind of dev tooling do you think would be the most helpful for developing with Halo2?
Yeah, I love that question. So the first thing I would point you to is on the Halo2 repo, we have a label for this, like dev tooling. I think it's just called dev tooling. But yeah, let me go back. Dev tooling. Yeah. Sorry, I also took my glasses off and I can't see anything. Right, okay. Yeah. This is the part that I didn't get into and I told you to go to Strat's talk, but not now. So right now, writing a Halo2 circuit is sort of a disjoint experience in the sense that the first part of your circuit is your constraints. And then the second part is assigning values that satisfy those constraints. So there's a very clear and intuitive link between those two parts, namely that given your constraints, you should be able to use them as a template into which you assign your values. And right now we don't have this link, which means that we're more or less assigning values freehand and hoping that we translated the constraints correctly over to value assignment. So this is, it can introduce a lot of bugs and a lot of frustration and a lot of unnecessary developer hours. So for me, that would be one of the biggest improvements to developer experience. It's a better link between the configuration and assignment parts of writing a Halo2 circuit. So by the way, I think that's also closely linked to finding a better intermediate representation, or DSL, but that's a longer-term project, which I hope would involve many other implementations as well. Another improvement to developer experience would be an improved layouter. So, okay, Strat would have explained this in his talk, but basically a layouter is sort of a global strategizer that decides how to arrange different blocks or regions in your circuit, and in particular, how to pack them optimally such that you use the fewest rows possible. So right now, our layouter only packs things vertically. Yeah, it can shift things up and down, but it has no power to pack things horizontally, and that's because it cannot access the configuration, the number of columns that the user defined. So it cannot add or remove a column. And I think this is because of we've so far only implemented a simple layouter. And yeah, the next step would be to allow more sophisticated layouter strategies. And also hopefully to allow layouter strategies that, like I mentioned just now, serve the fast prover or fast verifier use case. So the user should only have to specify what they're optimizing for, and the layouter should take care of the rest of it. Yeah.
Great.
Thank
Thank you
you
very much.